let's look more closely at the generators of SO3. Okay, so this is our next section. So are there any more questions about what we've covered? Okay, so the generators of SO3. So we call them Xi. In physics, and eventually that's the convention that we'll follow. In physics, we use Ji, which are defined to be I times Xi as the generators. Okay. All right, so, and that's because we like Hermitian matrices in physics. Okay, let's look at the generators of SO3. Now, if I consider my element infinitesimally close to the identity, which I wrote as 1 plus I delta theta dot x. Now, since this is part of SO3 or O3, we know that if I take its transpose and multiply it to the element, we get the identity matrix. So now if I insert this into this expression, we get 1 plus, sorry, I'm not using, why am I using I here? Yeah. I get 1 plus delta of theta, but here's a transpose dot x transpose. But of course, we know that the transpose of the identity matrix is itself. And the second factor is 1 plus delta theta dot x is equals to identity. Now, this equation is satisfied up to or linear order in theta. So we have on the left side, delta theta dotted with x transpose plus x. So it's this term multiplying this term and this term multiplying this term. And then we have a term which is multiplying this term and this term, but that term is going to be of order delta theta squared. Okay, so, and on the right hand side, we have the identity matrix. So from here, we get the equation that delta theta dot x transpose is equal to minus delta theta dot x. Now, delta theta I are all small but arbitrary, right? So, so it must be that this equation, for this equation to be true for all these arbitrary values, it must be that each of the generators are antisymmetric. Okay, so we have found one of the properties of the generators, that they are antisymmetric. Now, the other property that's important for us is that since we know that G of theta has the form of E theta dot x. Now, if I take this determinant, this is +1, and this is, theta I trace of xi. So that means that the trace of the generators must be 0, so that this thing is 1. So we see that xi are traceless. So these are the two properties of the generators of SO3. Okay. So let's look at a convenient choice. So let's call this x1. We'll come to their geometric interpretation in a moment. So x1, this is the first, row and column are 0. And x2 will have its second row and column 0. And x3 will have its third row and column 0. Okay? So, so these generators, I'm going to write the physics because that's what we will be using. Okay, let me, this implies that the JIs satisfy, and that's something you should do for yourself. And it's, if you take 2 of the J's and compute its commutation, you will get I times EIJK, J of K. Okay, so where I and J and K, these are indices which go from 1, 2, then 3. Okay, so and what is epsilon? Epsilon IJK. This is a symbol which has the following property. So it's called the Levi-Civita symbol. It's also sometimes called a tensor, although it's actually not a tensor. It is what is known as a tensor density. So this is 1 for even permutations of I equals to 1, J equals to 0, K equals to 0. Okay, so for example, okay, let me just first give you the definition. And then it's -1 for odd permutations of I equals to 1, J equals to 0, K equals to 0. And it's 0 otherwise. So this means that, for example, E123, oh, sorry, what am I saying? Sorry. E equals to, I equals to 1, J equals to 2, K equals to 3, okay? Yeah, I equals to, J equals to 2, K equals to 3, okay? So for example, E123 is 1, then E epsilon, say 213, what would it be? How many permutations do we need to go from here to here? Just 1, right? So that would be -1. But if I write, say, 231, then I basically have to do 2 permutations. So that would be 1. Okay. But if you have 1, 2, 2, that's going to be 0. If you have 2, say 1, 1, that will be 0. So any index, if it's repeated, then it's going to be 0. Okay, so then E2, 3, 3, etc. These are 0. Okay, so this is the Levi-Civita symbol. Have you guys seen this before?
Yeah, I saw it before.
Anyone who hasn't seen this before? Okay, this is essentially the object behind cross products. Okay, so if you have, say, V is equals to, say, some vector A cross B, then the kth component of V is essentially given by ijk aibj, okay? And there's a summation involved, implied. The summation over I and j are implied. Okay? All right, so this equation it's pretty important. So let me box this up. It's called the Lie algebra of SO3. Okay, so here, Einstein, there is a sum over K. Okay, although you don't actually, well, in this case, there is no sum because if you choose I and j to be different, because otherwise it's going to be 0, then K is, the value of K is fixed to be 3. Okay, so this equation is called the Lie algebra of SO3. Okay, so this is named after a guy called Sophus Lie. This is not Lie. So, okay. And the Lie algebra will be a frequent character in the rest of the story, in the rest of this course. Okay. All right. So, any questions so far? Yeah.
Are x1, x2, and x3 related to the Pauli matrices?
They are related. Yes. The Pauli matrices are going to be, the J's are going to be, I mean, the J's are more closely related to the Pauli matrices than the X's because, so, I mean, you can express this now in terms of, say, X's, right? Then you'll have commutator of Xi and Xj is minus epsilon ijk xk, right? Did I get all of right? Yeah. And then this is going to be this is the mathematician version of this Lie algebra, right? So you can see that when we look at the Pauli matrices actually have this algebra. So you're right. But what you can show is that the Pauli matrices is a particular representation of this algebra. And actually, it's the other way around. Depends on your point of view, but this algebra with the specific J's that we have chosen here, like these X's, and let me also write the J's here. So J1 is going to be as you can see, if you look at this 2x2 component, and well, actually, that's not a good thing. Not a good way of looking at it. The J1, J2, J3, they're going to be a representation of the Pauli algebra. Okay. So I think this is a good place to take a break, and so we have 2 more minutes before we go on a break, but are there any questions or comments, or maybe I made some corrections?